Okay, so we have this formula for the covariant derivative of a covector field in terms of the induced parallel transport structure on the cotangent spaces. Now we want to use our definition of the covariant derivative of a vector field, which we know we have this definition from the linear connection on the tangent bundle, okay? And we know that if we take the covariant derivative of a vector field, we can express that, like nabla xy, we can express that in terms of the parallel transport maps by a similar formula where essentially we take this difference quotient, we take the limit as t goes to 0 of p gamma from 0 to t inverse of y at gamma of t minus y at gamma of 0 all over t. Okay, so this is just the covariant derivative of the difference quotient in terms of the parallel transport structure here. Okay. All right, so you can pause the video. I have that already because we've been given a linear connection on the tangent bundle. So now we're going to rewrite this difference quotient that we've kind of used to define the covariant derivative of a covector field. We're going to do some algebra and rewrite this difference quotient such that it kind of mimics the form of the difference quotient for the covariant derivative vector field. And then in doing so, we can solve for the expression of nabla x of omega evaluated at a vector field y. We can solve for that in terms of the covariant derivative of y, okay, which we know we've been given. Okay, so how is this done? Well, I'll just show you the computation. It's an algebraic computation. Okay, so you can see, okay, we start with the difference quotient, which we've used in our definition. Okay, and then first step is we apply this the definition of this dual map of the cotangent spaces, okay, that we described earlier. So we get that our difference quotient becomes the limit as t goes to 0 of omega gamma of t p from 0 to t of yp minus omega p at yp all over t. And then we essentially we add and look at the numerator here and add and subtract omega at gamma of t of y evaluated at gamma of t, okay? And then essentially we do some algebra and factor this and kind of use a trick where we write y at gamma, where we write this term y at gamma of t as p gamma from 0 to t, p gamma inverse from 0 to t of y gamma of t, okay? So we essentially factor out omega at gamma of t and rewrite the expression in such that it algebraically mimics the definition of the covariant derivative. And then in doing so, we can solve for this covariant derivative nabla x omega evaluated at the vector field y, and it's namely nabla x of omega of y minus omega of nabla xy. Okay. All right. So this kind of algebraic process, which I kind of skipped through, and again, if you want to see the details, you can just go ahead and pause the video, and the details are right here. Okay. So we obtained the formula for the covariant derivative of a one form, namely nabla x omega evaluated at the vector field y is equal to nabla x of omega of y minus omega of nabla xy. Okay. All right, but there's a couple different. So that's how we get that's how we obtain the kind of the covariant derivative of a covector field given a linear connection on the tangent bundle. So from a linear connection on the tangent bundle, we can kind of construct a linear connection on the cotangent bundle. And it turns out that this method of constructing the linear connection on the cotangent bundle is quite special, and and for various reasons that we'll discuss later in this video. But for now, I want to provide you with a couple ways of remembering this formula. So there's actually different ways to arrive at this formula for the covariant derivative of a covector field. Okay? And the best way to remember it is essentially you take the covariant derivative of the identity map. And I'm skipping ahead a little bit here. Okay, so let me not give you this. I'll give you a better way to remember this formula later on, because I don't want to skip too much material. So now we need to kind of generalize this process for an arbitrary tensor bundle. Okay, so given a linear connection on the tangent bundle, we're going to use a similar idea to construct a linear connection on the tensor bundle, on the RS tensor bundle. Okay, so to do so, we just need to kind of generalize the parallel transport maps. Okay, so for every parallel, so given this linear connection, we have a way to parallel transport from, let's say, t of gamma of 0 of m to t gamma of t of m. Okay, we also have a way to parallel transport covectors t star at gamma of 0 to t star at gamma of t. Namely, it's the inverse of this dual map. Okay, so you take the dual, which gives you a linear isomorphism from t star at gamma of t to t star at gamma of 0 of m, and then you take the inverse of this map, which gives you a linear isomorphism from t star gamma of 0 of m to t star gamma of t of m. Okay, so now we have this basically p gamma 0t, so p superscript gamma subscript 0t, and then we have p star inverse. Okay, and these are maps respectively. The first one is a linear isomorphism from t gamma of 0 to t gamma of t of m. The second one is a linear isomorphism from t star at gamma of 0 of m to t star at gamma of t of m. Okay, and using these two linear isomorphisms, we can actually construct a linear isomorphism, or not a linear isomorphism, a multilinear map. Okay, a multilinear map on the Cartesian product, where we just take so we take the, let's look at R vector field, so R copies of the tangent bundle and S copies of the cotangent bundle, take their Cartesian product, okay, and then evaluate it at gamma of, all of those are located at gamma of 0, and then we send that to R-fold Cartesian product copies of t gamma of t of m, Cartesian product with S copies of t star gamma of t of m, and we just send we send R vectors and S covectors to R vectors and S covectors component wise using these linear isomorphisms, p 0t and p star inverse 0t. Okay, now it's important to note that these that a priori these parallel transport maps do depend on the curve gamma, but after deriving these formulas explicitly in terms of the vector fields, like what we did previously, for just the covariant derivative of a covector field, it's very important to note that these definitions are independent of the given curve gamma. Okay, but the parallel transport maps are not. Parallel transport depends heavily on the curve gamma, and if you choose different curves gamma, then your parallel transport is going to be different, even if you are parallel transporting between the same 2 points. However, we're just using this parallel transport as a way to conceptually define this covariant derivative, but the ultimate formula is going to be independent of the path, because it's only going to depend on the on these linear connections. Okay. All right. So back to our discussion, we have a multilinear map from the Cartesian product of r copies of the tangent bundle and s copies of the cotangent bundle at gamma of 0 to this this same Cartesian product of r copies of the tangent bundle, s copies of the cotangent bundle, now at gamma of t. We have this parallel transport isomorphism, or not isomorphism, but a multilinear map, but it factors through to the tensor product by the universal property of the tensor product, factors through and gives us a linear isomorphism on the tensor product, okay? All right? And is it multilinear? Now I'm trying to think, how does this factor through the tensor product just algebraically? So I think the codomain should be the tensor, actually the tensor product space. And then, yeah, okay.